Great. Hi, everyone. We're going to have two talks on FRBs as probes. The first one is going to be by Xiaohan Wu from CITA on FRBs as probes of the CGM. And the next talk is going to be by Jon Sievers on FRBs as probes for cosmology. So two interesting topics. And keep in mind, after these two talks, we're going to have breakout sessions. You have to choose whether you're interested in FRBs as probes of stellar astrophysics or galactic astrophysics or cosmology. So keep that in mind while you're, watching these talks. Thank you.
So as you can see from the schedule, my suggested topic is to talk about astrophysics, but I don't study all these grand stuff. I only study the circumgalactic medium. So I'm only going to talk about the CGM. Here's a very nice figure from Drummond Fielding, which shows an analogy between the circumgalactic medium and the Earth's atmosphere. So basically, what this is showing is like the circumgalactic medium is almost like an atmosphere around halos, just like the atmosphere around the Earth. So the physics, the current consensus of the physics in the CGM is like you have gas inflow from the IGM, which cools down and then triggers star formation. And then after star formation, you have feedback, which triggers gas outflow. And then you have like all the complicated physics, which triggers multi-phase condensation. So you have like a mixture of cool and hot gas in pressure equilibrium with each other. So that's like the basic picture of the circumgalactic medium. And then immediately you see that the properties of the CGM is basically shaped by the galaxy formation process. So here's a comparison between illustrious and illustrious TNG. So basically these galaxy formation simulations, they are calibrated using the Redshift 0 stellar mass function. So if you look at the stellar column density shown on the right there, they are very similar between these two simulations. However, the feedback mechanisms are pretty different. So if you look at the gas density and gas temperature shown on the left and the middle, you see they are vastly different. So basically, illustrious is better at expelling gas out of the galaxies. So the gas is like, the gas density is lower around galaxies and the gas temperatures are higher. And therefore, this is just showing the CGM can be a very powerful probe as galaxy formation models. So in addition to probing galaxy formation models, the CGM can also help us map the missing baryons. So what the missing baryon problem says is that you have this pie chart, which is the expected amount of baryons that we should see in the universe. But with different probes of the baryons in the universe, you only observe like 70% of the expected number. So where are the rest of the 30% of the baryons? So the consensus is that the missing 30% is very possibly located in the hot phase of the CGM. So by mapping the distribution of the circumgalactic medium, we can possibly resolve the missing baryon problem. So traditionally, the oldest way of measuring the circumgalactic medium is through the quasar, the metal absorption lines in the CGM in the quasar spectrum. But then there are like a lot of limitations to this method because you have to make some assumptions about the metals. And then the metal absorption lines, they are basically just tracing the highly ionized and enriched gas in the CGM. And then this method has been like going on for decades, but right now I still don't think there's like a very clean method of analyzing the multi-phase CGM. And then people are still just calculating the column density of these absorbers. So besides the metal absorption lines, there's also the X-ray observation, which is able to probe the hot phase of the CGM. But the problem here is that the X-ray luminosity depends on density squared. So this method is almost only applicable to galaxy clusters. There are current efforts doing X-ray stacking on like star-forming galaxies, but this is, as you can see, extremely hard. And then the Stanislav-Sadovich effect of the CMB is recently getting very interesting because of some efforts within the Atacama Cosmology Telescope. They're doing some interesting stacking measurements of the thermal and kinetic SC, and they are getting some useful constraints on the circumgalactic medium. But the problem here is that for thermal SC, it depends on halo mass to the 5/3. So again, it is dominated by the most massive objects in the universe. And then for kinetic SC, it only depends on the electron number density to power of 1. But you have to rely on a reconstruction of the underlying density field. A reconstruction of the velocity field. So then you can correct for the effects of the radial velocity. So there are limitations to all of these methods. But fortunately, we have fast radial bursts, which are going to give us a new possibility of studying the CGM. So here the idea is very simple. If you have an intervening CGM between the FRB and us, then the intervening CGM will give you an excess contribution to the total DM. So by measuring the DM from the intervening CGM, you can measure the distribution of the CGM. And then the nice thing about using FRBs as a probe of the CGM is that the DM is only dependent on the number density to power of 1. So you are actually going to be able to measure the CGM for lower mass objects, which is not so doable for like thermal SC or X-ray studies. But the problem with measuring the DM from the CGM comes from the uncertainty from all the other terms in the total DM. So for the host DM can vary from like a few tens to up to a few hundreds. So it's highly uncertain. And then the DM from the IGM, if you have localization, you can probably estimate it by integrating the mean electron number density as a function of redshift. But if you don't have localization, then you know nothing about it. And then the DM from the Milky Way, it's also uncertain, but you can probably estimate it based on some sorts of models. So the way to deal with this uncertainty is actually to do stacking. So what that means is that if you have a sample of FRBs that have CGM intersections, you can calculate their mean DM, and then you subtract off the mean DM of the sample of FRBs without CGM intersections. So then you have a very simple estimator of the DM of the circumgalactic medium. So previously, people, when theorists proposed this idea, they assume that the FRBs are localized, which means that you can get an estimate for the DM from the IGM in an average sense. So then people predict that with order 100 FRBs, you can get a pretty decent constraint on the DM from the CGM. But the problem in my project is, what about unlocalized FRBs? So specifically, we were looking at whether we can constrain the DM from the CGM using the CHIME first data release. So this is also following the previous work by Liam Connor and Vikram Ravi. So the problem with CHIME is that you have a huge localization error, 0.2 degrees. So the way to beat this is you want to beat the magic with a magic. So you just select very nearby halos that span an even larger area on the sky. So very nearby means that we selected 10^11 to 10^13 solar mass halos within like 40 to 80 megaparsec. And then we measured the, we were targeting impact parameters below 1 to 2 RVR. So then we wanted to use the simple estimator to calculate the DM-CGM, the sample mean DM of the FRBs with CGM intersections minus the mean DM of the entire CHIME sample. So the problem here is that for CHIME, you don't know anything about the localization. So that means that you can have that kind of a huge high DM tail in the DM distribution. So in the right plot there, I'm showing the DM distribution of the entire CHIME sample as the black line. And then you see the all the tail of the high DM FRBs, and those are potentially very far away. So in my work, we actually want to get rid of all these high DM FRBs because the sample size is pretty small. You only have like 500 FRBs in total in the CHIME first data release. And then there are maybe like 20, 40-ish FRBs that actually have CGM intersections. So if you have a FRB that is like having DM of over 2000 in the sample that has CGM intersections, then it's going to contribute to like a DM excess of over 100. So that's going to significantly bias the sample mean DM. So we want to get rid of all these high DM FRBs. And then what we did is that we proposed to do a weighted stacking method. So we used a weighting function that looks like the red line shown in the right-hand plot there. What that does is almost like it's cutting off all the high DM FRBs of DM larger than roughly 600. And then instead of the unweighted sample mean, we calculated the weighted mean DM for the FRBs to estimate the DM from the CGM. So then this is the money plot of our paper. This is showing the DM from the CGM as a function of impact parameter normalized by the halo viral radii. So we divided the halos into two samples. One is 10 to the 11 to 12 solar masses. The other is 10 to the 12 to 13 solar masses. And then we have 3 radial bins for each of the halo samples. And then the points with error bars, these are the measurements. The lines are comparisons with different models taken from Ian Williams' paper. So the conclusion is basically that we find like a 1 to 2 sigma detection of the DM from the CGM, which is a pretty low signal to noise level because we only have like such a small number of FRBs. And then because the methodology is different from the Connor and Ravi paper, we get a lower signal to noise level of detection. But then I want to stress that because you know nothing about the localization in CHIME and you have such a large localization error, the weighted stacking scheme is actually going to be very important if we want to push this methods forward to using more CHIME data to measure the DM from the CGM for these nearby halos. So in my paper, I actually did a calculation and we predicted that with like a few thousand more FRBs from CHIME, we can get like a 4 sigma detection of DM from CGM using the weighted stacking method. And then I also know that in CHIME, you have those Archimedes localized FRBs. So with that kind of localization, you can actually push the galaxy selection criteria to 10 times further away. So that's also going to give us more signal to noise level. But then we'll have to coordinate the efforts here because I know people are also interested in doing similar stuff with these Archimedes localized FRBs. And then for a far away future plan, like when you do have the localization data, you can actually subtract off the estimate for the DM from the IGM and then do the unweighted stacking. So that's going to be more interesting than the current sample. And then you can also just do like a forward modeling of each component of the DM when you have like really well localized FRBs. So as an example, I mean, different people have mentioned this in different talks, so I probably don't have to go into details, but a flim-flam survey is going to target 30 FRBs, very well localized. And then it's going to measure the redshifts of galaxies within 1 degree of each FRB, and therefore reconstruct the underlying density field. So they're going to get a very good handle of the DM from the IGM because they are actually going to reconstruct the cosmic web. But the problem is that really going to be so useful? So in my opinion, I think it's not as useful as low DM FRBs because these FRBs are like extremely, just very high redshift 0.2 and above. So in my opinion, it's probably going to be more useful to target low DM FRBs because you can actually you get a very it's not only because you get rid of the DM from the IgM completely, but also because you get a much better handle of the DM from the host. Like a very good example of this is the FRB from the M81 globular cluster. Like there's no contribution from the M81 disk, so you only have contribution from the M81 host and the Milky Way host. So the total DM is actually placing a very interesting upper limits from the CGM of these two halos. And by the way, M81 and Milky Way has pretty similar halo masses. So in my opinion, this is going to be more useful. And also because in our weighted stacking scheme, we are also effectively just using the low DM FRBs from the nearby universe. So I want to use the last 5 minutes of my talk talking about a different thing, which is an ongoing work. I don't have any results to show you, but it's going to be useful for like FRB scintillation and gravitational lensing as well. So I want to mention it here. So here, the problem we want to target is the multi-phase CGM. So as I mentioned very briefly earlier, the CGM consists of two phases. One is a hot phase, 10 to the 6 Kelvin for a Milky Way size halo. And then there's the cold phase, 10 to the 4 Kelvin, 10 to the 4 Kelvin. So the picture here is that the cold phase is like tiny cloudlets, like the raindrops embedded in a hot phase, which is the hot diffuse gas. And then these two phases are in pressure equilibrium with each other. So the arguments for the existence of these clouds, these cool clouds, is very similar to the physics of the Jeans mass. So basically, you just want to calculate the sound speed times the cooling time as an estimate for the size of the cloud. And then that's going to give you like roughly 0.1 PC. So this is like an order of magnitude estimate for the size of the cloud. And then what's interesting about these cool clouds is that they can act as plasma lens for the FRBs. So here's a very simple model that illustrates how the plasma lens works. So on the right, I'm showing with a blue circle as an illustration for the cool cloud in the CGM. And then as the light travels through the cloud, it's going to, the phase of, as the radiation travels through the clouds, it's going to, there's going to be an advance in the phase because of the plasma in the cloud. And then you'll see after the radiation travels through the clouds, there's going to be a tilt in the wavefronts. And that's shown by the yellow curve on the right there. So immediately you see that because of the advance in the phase of the radiation, the plasma lens is diverging because the shape of the wavefront is shaped like that. So it's the opposite of gravitational lensing, which is converging. Yeah, so this is what we call by plasma lens. It's a diverging lens. And then you can estimate the deflection angle of the plasma lens by calculating the gradient of the phase across the cloud. And then you can also calculate the time delay, which is proportional to the deflection angle squared in the small angle approximation. So in the Vedanthan and Finney paper, they did this calculation and they estimated that for a 0.1 PC cloud with column density of 10 to the 17, you can possibly get a 0.2 milliseconds time delay, which seems to be a pretty large number. So these authors, they predicted that for FRBs, you are supposed to look at the scattering tail of the FRB and look for this kind of time delay. But in my project, we think this is not going to be the interesting thing to look at because you're not going to be able to tell apart whether the time delay you see in the scattering tail is from the host or from the intervening CGM. So what we think is going to be interesting to measure is actually scintillation. So here's a very simple toy model that illustrates the idea of FRB scintillation. So again, the blue circle shows the cloudlets in the CGM, and then the FRB is shown by the yellow star at the top. So as I mentioned earlier, the plasma lens is diverging. So you see, if you're in the correct range of parameter space, you're going to see 3 images, and the images are shown by the cyan stars on top of the CGM cloud there. And then there's another scattering screen down on the top, no, down in the bottom. That's the Milky Way scattering screen. So that's what's going to give you scintillation. And by the way, scintillation basically means the twinkling of the stars. So the idea here is that the Milky Way scattering screen is going to give you some short timescale scintillation. And then when you have 3 images, the 3 images are going to scintillate on their own, like almost independently. And then the images are going to arrive at us at different times at a longer time scale, which is the delay time. So then if we calculate the autocorrelation function of the FRB intensity as a function of frequency, so here you want to translate the frequency, you want to translate the time delay into a frequency by just inverting the time delay. So then if we assume that the 3 images have equal magnification, the amplitude of the autocorrelation function will be 1/3. Because we are assuming the images are going to scintillate independently on their own. So I know this is probably not very clear, but you can ask me later on if you're interested. But what this is basically saying is that by measuring the autocorrelation function and then doing some theoretical modeling, we can actually constrain the size, shape, and density of the clouds in the CGM. And then what's also cool about this idea is that because the cool and hot phase are in pressure equilibrium and their temperature ratio is 100, that is basically telling us the density ratio is also 100. So if you're able to measure the scintillation as a function of impact parameter, then you're also going to be able to constrain the density of the entire CGM. And then I want to say that this scintillation stuff is also going to be useful for gravitational lensing and what do I want to say? Yeah, just gravitational lensing. So I think I'll stop here and take questions.
We have time for questions.
I have 2 questions. One, regarding you were saying that, it's the scattering time is not going to be very useful for constraining the cloudlets in the CGM because scattering could also come from the source, if I understood you correctly. But if you assume something about ISM of galaxies, and we live in one, so we do know what ISM. And unless you want to posit that FRBs are in some very, very unusual locations, then you can sort of model what distribution, at least on a statistical basis, what distribution of scattering times you might have, especially since you also have the dispersion measure. So somehow scattering dispersion measure relation is something, with reasonable assumptions about the ISM, the galaxies, you might be able to test versus, I would think, the CGM. And that's something that we did try to do in a paper led by Pragya Chawla in looking at the distribution of scattering and DM properties. So I just wondered, do you think there's no hope really for doing that? Well, that's question number 1. And the second question is really easier, is you mentioned that it was in the era of chord that we would have on the order of 100 to 1,000 well-localized FRBs, but that's actually, I think, if I understood what you're looking for correctly, chime FRB, the outriggers are actually going to achieve that sooner than chord. And so that would be, I think, of use to you as well.
Yeah, I wasn't really paying attention to outriggers, but yeah, I think it's going to be very cool. And then, so I wasn't really paying attention to like the modeling of the scattering time, but yeah, most of my reference just comes from Keogh's paper in 2015. And then in that one, the I think the scattering tail is like 1.6 millisecond. So that's like really large. And then, I mean, it's really not going to be able to tell like whether that comes from the host or the clouds in the CGM. Yeah, but yeah, I agree. Some kind of modeling will be useful.
Hey, that was a really nice talk. Thank you. So for the missing baryon problem and going after the DMs of the CGM, you've basically described three methods. The first is a sort of flim-flam DSA method, where you're probing the DM from a CGM of an intervening galaxy with a localized FRB. The other is the unlocalized case, your and our method. And then finally, the low DM one. And you say the low DM one is maybe the most constraining. But there you're not making a detection. All you get is an upper limit for the CGM of the Milky Way and the host. So yeah, I wonder if you could expand on that a little bit. You're really only measuring the CGM of one galaxy, and that's the Milky Way in that case, even though it's a much cleaner measurement. Agree?
Yeah, I mean, I just feel like even if you get a very detailed modeling of the cosmic web, you still have like a huge number of uncertainties, like the host, for example. So yeah, I just feel like even if you're just putting an upper limits using the low DM FRBs, it's still like very interesting constraints on the CGM. And then for the weighted stacking, because we are also effectively just using the lower DM ones, in that case you can calculate the DM from the CGM like relatively better, rather than putting an upper limits.
But one just follow-up comment would be, as the cosmologists keep telling us, as Keough keeps pushing, if you do a 2-point correlation function for the sort of flim-flam case, the DSA case, where you actually cross-correlate galaxy positions with FRB DMs, then the host galaxy should fall out in some sense. And it becomes more like the stacking analyses that we did.
Yeah.
Yeah, that was a fantastic talk. Thanks so much. One of the areas that I really found interesting was the cloudlet analysis. But one of the questions I did have is, so we see in simulations and in a bunch of absorber studies that there's medium scale structure in the CGM where you have significant outflows coming from feedback from within galaxies. But I'm just curious as to have you thought about how disentangleable smaller scale denser structures would be from larger sort of intermediate scale sort of kiloparsec, tens of kiloparsec structures than the CGM would be?
Yeah, that's an interesting question. Yeah, so I'm not exactly sure. I guess if you have like observations of very nearby stuff like the Milky Way or M31, you can probably get a better handle of like the outflows. But for if you're just focusing on like the plasma lensing stuff, then you have to require like tiny things in order for the plasma lens to work. Yeah, so we actually worked out the criteria to get the range of parameter space to get to get the 3 images, and then it's like you have to rely on cloud sizes smaller than 0.1 PC, and then column density is higher than, for instance, 10 to the 19. So it's actually very hard to get plasma lensing to work.
Sure.
There's a question online. If it's a short question, we'll take it.
Yeah, it's a follow-up question on the cloud size again. Thank you for a nice talk. Yeah, so you said only small screens. You explained the scintillation effect from the perspective of just 3 images, and why would you assume that 3 images are? I mean, you can have like more than maybe a million images that can come interfere and produce the scintillation. So, my question is like, why do you think you need a small screen again to produce plasma lensing?
Sorry, is the question why is there only 3 images?
No, my question is why do you have a small screen constraint to produce scintillation of FRBs?
Oh, I mean, the scintillation comes from the Milky Way scattering screen.
Yeah.
Yeah, so it's effectively just a 2-screen or even 3-screen system.
Okay. So you expect you're saying that we can't have scintillation from the host galaxy. We can only expect scattering from host galaxy screens. I'm talking about host galaxy screens.
Sorry, I'm not super understanding the question.
So I was thinking, is it possible to produce scintillations with host FRB host galaxy screens? For example, cataclysmic environments of FRB, FRB local host.
Oh, I see.
Yeah.
I guess probably no, but I guess there are other experts of scintillation in the audience. So yeah, I'm not exactly sure. I think it's no. Can we produce scintillation in the whole screen? Yes? Oh, okay.
All right. So we can have large screens there, or do we have a screen criteria there too?
Yeah, it sounds like it's yes.
We can have very large screens. So will you have a point source criteria being satisfied there? Like if the screen is close by to the source, you don't have a.
Sorry to interrupt. I guess it's a great topic for discussion offline. So
Yeah.
let's thank.
All right. Sorry. Thank you.
All right. Our next speaker is Jon Sievers from McGill. He's going to be presenting remotely from McGill soon.
Hey everybody, sorry, I'll get my screen shared. And I apologize in advance. I have come down with a cold. So I've got my tea and my box of Kleenex. So if I disappear hacking away, I apologize, but it may happen. Okay, so thanks to the organizers for inviting me to talk. And I'm going to talk about FRBs as probes of cosmology and fundamental physics. So I also want to thank, I thought I had a success-oriented talk, but Xiaohan covered a lot of the IGM, ICM material, so I want to give less background, so thank you for that. Right, so what do we know about FRBs? And does it matter if we don't actually know what they are? Well, I don't think I need to remind people here that they give us an exquisite redshift weighted line of sight column density and exquisite timing. They're very close to lambda squared. And another thing I'm not going to talk about, they measure Faraday rotation very well if you have linear polarization. So I'm also going to assume, basically talking about this, that we're going to be living in a world where we have lots of localizations. We've got a handful now, but as Vicky said, with chime outriggers coming online, in the space of a not very many number of years, we're going to have probably hundreds, many hundreds of localizations. And that really changes what you can do. And also put in my usual, so if you're talking to a cosmologist, no cosmologist knows what DM is, but they know what the Thomson optical depth is. And reminder, that conversion factor is 500,000. So if you say, oh, I have a DM of 5,000, you can just tell a cosmologist, oh, that's a tau of 0.01, and then they'll understand you. Right, so very, very quickly after FRBs were discovered, people started thinking about them as probes of cosmology. So this paper was out within a year or two of the first FRB announcement when there was only one. But it was very clear early on that, as Xiaohan said, there's a lot of potential to track down what gas is doing. And in fact, I was going back and looking through the literature. The first copycat paper of this one came out within like another month or two later. So it happened very quickly. I'll come back to this a bit later on. But again, like Charles said, 100 FRBs might be enough to do it. Okay, so let's go through what we actually measure, which will actually be useful in thinking about how we're going to maybe do some cosmology or physics with this. It's what we quote is the dispersion measure, which is equivalent to the low redshift column density. But at high redshift, the frequency goes up by 1 plus z, and since delay goes down like nu squared, we shrink the effective importance of plasma starting out with there by a factor of 1 plus z squared. But of course, if I have a delay in time from going through a plasma screen of some delta t, as it gets closer to me, that gets boosted by another factor of 1 plus redshift. So what we're actually measuring is the electron density over 1 plus z dx. So if the ionization fraction is constant, which may be true, then we pick an extra factor of 1 plus z cubed for the density at redshift z, and we'll write, you can do this many ways, but we'll write dx is c times dt dz, because dt dz is something that's pretty, the time dependence of redshift is something that's pretty easy to get from cosmological calculations. So that means the thing we actually observe is the integral of the density today of electrons times 1 plus z squared times c times this dt dz factor integrated over redshift. And this is where the cosmology will come in for sort of large scale things, is that dt dz thing. So we've all seen this plot before, is that if you talk about low redshift, where low can be up to a few, it is this relation for current cosmology parameters is like shockingly close to linear. Like I have no idea how it comes out this flat. If you do, for instance, a flat matter universe, this is no longer true. So this is just something about the a curious fact about the densities that we have in our universe today. And the slope's close to 1,000. So if you just take the dm of something that you see and you think that dm is cosmological, divide it by 1,000, and that's the redshift. And so one of the fun things you can do with this in fundamental physics is talk about the photon rest mass. So say photons had a rest mass, well, E is gamma mc squared then, and you chunk through special relativity equations and let epsilon be the difference between the speed of a photon and the speed of light, the fractional difference. And you work this through, and you get that fractional speed difference goes like a half times the the photon rest energy divided by the h nu, the photon actual energy squared. So this looks like a plasma delay, which unfortunately will make it a little bit harder to make huge constraints on this. But we can do pretty well. So if we assign all of that delay to a photon mass, if we have some high redshift FRB, so if we take a gigahertz and a dm of 1,000, then the time delay is about 4 seconds. So the fractional difference in speed between the propagation speed of the radiation and the speed of light is about 2 times 10 to the minus 17. So it's exquisitely close to the speed of light, even if you say all of this dispersion is due to photon mass. Now, unfortunately, the mass, the delay goes like the mass squared, so the mass goes like the square root of the delay, so you lose a lot from that. But you still end up with constraints on the photon rest mass of about 2 times 10 to the minus 14 electron volts rest energy, or about 5 times 10 to the minus 50 kilograms. So this is competitive or better than the best lab limits. So actually already just the simplest thing you could possibly do with FRBs gives you some of the best limits on photon masses out there. And of course, now that we know how to calculate dm of z, the photon looks an awful lot like that, except you don't get this 1 plus z cubed factor from increasing density. And so if you look at this as a function of redshift, then delay, the blue curve is the delay, this is sort of the equivalent dm from the photon rest mass versus redshift, and looks very different than the standard plasma delay. So if you have a large population with redshifts of FRBs, then you should be able to do a fair amount better. Now, unfortunately, I said like there's uncertainties there, and you only win as a square root of the delay, so it ends up being about a factor of 10 improvement. So this is a paper from a couple months ago where they've done that, and they do about, one signal is about a factor of 10 better over the sort of a naive thing. So we have to do a little bit better, but I think it's kind of neat that already we have best direct limits on photon mass. There are indirect ones, which maybe I'll save for questions if anybody cares. Similarly, one of the foundational principles of modern physics is the equivalence principle, which says that that gravity and acceleration look the same. So this is the weak equivalence principle. The strong equivalence principle also says that gravity is independent of velocity. But we can test the weak equivalence principle quite well. And the way this happens is that if I have a photon coming out of a potential well, if equivalence is violated, you would expect that the Shapiro delays would be different for photons at different frequencies. And so the arrival as a function of frequency would look different. Excuse me. And that will tell you, that'll constrain equivalence principle. So people have been talking about this for a while, but a nice paper came out a month or two ago doing this, and they get a nice limit. They say it's very hard to do right, and there've been a lot of wrong papers, so be warned. But that the limit on the Newtonian violation is the mass gravity acceleration equivalency is 10 to the minus 13 for the non-Newtonian parameter, and these are the best constraints in this low mass region. So just right away, we can get some pretty cool basic physics out of FRBs, just because we can measure their relative arrival times, their fractional arrival times to something like part in 10 to the minus 17. So I've shown the low redshift DM of Z relations. So here's extending that same thing, again, assuming constant ionization fraction out to higher redshift. And now it no longer looks like a line. But as you see, like if we start pushing out to redshifts 5, 10, 15, we get DMs of several thousand. And I put in, if you care, a couple of handy rules of thumb for if you're going to higher redshift, what the DM should look like. And again, the coefficient here assumes Planck parameters, assumes that hydrogen is fully ionized and helium is not ionized, and that no electrons have gone into stars. Of course, that may not be the case. So, there's uncertainty in helium ionization, but at some point, if the universe has enough hard photons, then helium will ionize, and we'll see an injection of electrons into the universe. So here's a paper by Eric Linder from a couple of years ago showing what this might look like if you have helium ionization at different redshifts. So that's what's going on physically. And you can go even to higher redshift. If you go back here, you start saying we're looking at FRBs at DMs of 6 to 8,000. Now, if that's a cosmological DM, then we're starting to probe ionization. And we can directly that. So here's a nice paper updating limits on this. And if you have sort of order 100 FRBs from redshift 5 to 15 with localizations and redshifts, then you can actually measure the optical depth of reionization and the reionization history pretty well at a level that improves CMB measurements. So for instance, one of the big degeneracies in the CMB is that the optical depth to reionization is very degenerate with the power spectrum amplitude. And so this is how uncertainties on things like sigma 8 show up. So we might understand sigma 8 better if we could measure this reionization from FRBs. And so, it's another case where high DM FRBs might be very interesting. So you might ask yourself, with all these precise measurements, can we do precision cosmology? Because, as you see here, well, DM of Z changes in different universes. So can we measure that? So this is work that Tony Walters led and collaborated on a few years ago. And we started out saying what we were going to measure in cosmology with FRBs And after we actually went through the work, well, after Tony went through all the work, what we said was, what we're going to measure is the star formation history of the universe, because the uncertainties in the fraction of baryons that are out and about versus in collapsed objects is more uncertain than our uncertainties in cosmology. So, that's why something like this, the helium ionization, probably will be very hard to do, because different star formation histories could end up looking a lot like this. Although I'm a lot more optimistic about the ionization. So, people do periodically talk about trying to do precision cosmology, but it will be very hard, because what you measure is the integral. You measure the integral of electron density times this dt dz, but that density does depend on astrophysics as well as cosmology. So I won't say too much about this, but also, a way in that FRBs can be very exciting is that if you have things like baseband caches, you can probe time delays down, not like the days or weeks or months of microlensing or regular lensing, but now you can cross-correlate electric fields with themselves, and so you can start talking about nanosecond level delays. So there's some cool things you can do with that. Usual microlensing caveats apply, but it's pretty neat that when you've got this electric baseband data, you can just probe regimes that I don't think you can get to any other way. So these are slides now from Kiya Masui's, stepping back to more pure astrophysics, cosmology. We heard a little bit about these illustrious simulations, but just to sort of hammer home just how important and how uncertain what's going on with the warm, hot intergalactic medium is. This is videos now of illustrious and illustrious TNG. So the same team, same starting conditions, they've just updated their feedback mechanisms, and we'll see just how different the universe looks. And given that these are recent state-of-the-art, few years apart simulations, it gives an idea of just how uncertain what the universe actually looks like is with our current understanding. Starting to diverge. The right looks puffier. We start to see supernovas going off on the left that look very different on the right. And our blobs are even starting to evolve differently now. Now we have things that look like clusters on the right that are just missing on the left. So, the universe looks really different depending on what you use for feedback, and we really don't understand feedback very well. So, this is why it's so uncertain. Is if you've got gas that's cooling down, that gas cools radiatively, then it forms stuff, and that stuff gets spat back out, which affects the cooling. So it's a very, very sensitive process. And, does the gas get swept out, or does the gas not get swept out and gets to form and cool and make more things? So it's really hard to do right because this feedback disrupts the cooling, and that cooling is what sets the structure. So because a lot of the stuff is happening in low density environments that are hard to probe with things like X-rays, especially hard to probe with things like S-rays, it's really hard to actually measure this. And so that's where FRBs, one of the really powerful things we can do with FRBs. So this is the missing baryon problem. We don't think baryons are actually missing. We just don't know where they went because they're very hard to see. And we can't simulate it, and we have very limited tools to observe it. So FRBs mapping this out is a really valuable thing. they are useful for sort of low density IgM stuff, but they're also really useful, I think, for clusters, and that's because the optical depth through which clusters is very high. So the canonical number from SZ world is that the optical depth through a massive cluster through the center is a tau of about 0.01. So that's a DM of about 5,000. So there has to be a population of bright local FRBs with very high DMs that will probe cluster structure. And this is really nice because if we're getting 5,000 from the cluster and the other uncertainties are a few dozen from the FRBs, then we're talking about 1 or 2% measurements of the electron content of the intercluster medium content of clusters from single FRBs, and we're doing this electrons, components of the cluster that we have really almost no way of measuring. So this was proposed. I think the first paper I know of that proposed this, I was trying to convince other people to write one, but I failed to get there in time. It was proposed by Fujita et al. Back in 2016. And our own Liam Connor, along with the DSI team, just published a couple detections of FRBs that are probably inside clusters with XSDMs of several hundred that probably are starting to tell us something about cluster structure. Now, it's really hard to do this without localizations, and you really want the FRBs to be behind the clusters, not in the clusters, so you don't have to worry about where they're happening. But this is, I think, is a very exciting thing. And ACT got a shout out. So since that happened in the last talk, I didn't have a chance to put in the slide, but I did want to show this slide. So this is now data from Mustang 2, which is a 90 gigahertz camera on GBT. That's great for individual clusters. So if we get like a couple dozen FRBs in clusters, we could follow up all of those clusters here. And the advantages of this are that the resolution goes from like an arc minute or two, which sort of can see that it's a cluster but can't tell you anything about structure, to less than 10 arc seconds. And when you concentrate all your sensitivity on the cluster, which you can do with a large telescope but cannot do with a small telescope, you can make just exquisite maps of the SZ. So a few hours will often get us 50 to 100 sigma cluster maps in SZ. And the bottom right is from sort of a several dozen hour observation. This is the pressure profile now of a single cluster. And this, if you looked at this and you were from Planck or ACT or SPT world, you'd think this was a stack of hundreds of clusters. But we can do this for individual clusters. So if you've got clusters you want to do, you should come talk to me or the Mustang 2 team. And I will also add that because it's in the Northern Hemisphere, the GBT can see basically all of the region that, say, CHIME and CHIME outriggers would see, which is much harder to do from a Southern Hemisphere telescope. Okay, so we can do cool SZ things. This is the wrong talk. Oh, sorry. Yeah. Okay. Yeah. So we can also, another important thing is in cosmology. One of the big upcoming measurements from things like ACT, SPT, Next Generation CMB, Simon's Observatory, is going to be measurements of the kinetic Siniaz-Abdovich effect. And so that measures the product of velocity times density. And you really want to know about the velocity part of that for cosmology, but it's the densities along for the ride if you measure KSC. But so this is work that was led by Matt Avastral. If you've got, in the thousands type, tens of thousands types of FRB localizations, you can now start to map out what the density is doing of the IgM. And that lets you break the determinacy with the velocity to help you get at the cosmology you actually care about. And it also contaminates weak gravitational lensing as well. If there's matter out there that's clumping differently, that looks an awful lot like structure doing other things. And so if you understand this feedback, it's very hard to do percent level measurements of dark matter and thus dark energy. And again, I thank you for the slide. So it's really important to do this, this FRB tracing of the IGM. And again, I think this is really the only great tool we have to do this for things you might not even think about, like dark energy with lensing, cleaning up an important foreground. So, I apologize in advance if your favorite cosmology probe I didn't talk about, because there's a lot of things you can do with them. I think it's very exciting. But yeah, so just using the column density and the timing info with positions and redshifts, which again, the game is going to change very soon, we can probe an awful lot of things. And I do think that the high DM bursts are going to be especially valuable, both for the SC and for the reionization science. So if you're wondering if you should like push to make your pipeline efficient at high DM, I would absolutely encourage you to do that. And that's usually just a software problem, not a hardware problem. And so with this information, we can do things like constrain basic physics, rest mass equivalent, test equivalence principle. We can map out the missing baryons. We can break KSE degeneracy. We can look at distribution of electrons in clusters. We can do reionization. We'll have a lot of strongly lensed FRBs. We may get like just fantastic delays out of this. And I haven't even talked in the limited time I had about things like stuff you can do with RM, magnetic fields, or deviations from lambda squared, which lets you probe large density fluctuations, so highly dense regions. With low frequency telescopes, you may be able to see useful things there. So I'm going to stop with that and take questions. And thanks again for your attention.
We have time for 2 short questions.
That was a great talk. Thanks, John. So that was really cool stuff on the clusters and the ICM. I would just implore the Chime team to do some clever follow-up on all of your sources. We found 2 cluster FRBs in just 12 localized events. And I know the fraction will probably come down with time, but even if it's 5%, then you guys have hundreds of cluster FRBs. And I'm sure you could pull them out, especially with the arc minute localization. And then using things like Mustang, there's got to be some cool stuff you could do. Sorry, that wasn't a question, just a plea.
A plea I agree with.
Any questions online? No. Okay,
Right.
let's thank John again.
Thanks, everybody.
Now we are going to have a breakout session, right? A discussion. We have time, like 15 minutes. Yes. Okay, sounds good. Yeah, so there are 3 topics. FRBs as probes of stellar astrophysics, probes for astrophysics and cosmology. So let's form like groups here, rearrange yourself and have discussions among yourselves. We're going to have 1 breakout room online as well, right? Yeah.
There's similarly 3 breakout rooms online, so you can self-assign if you're most interested in stellar astrophysics or FRBs as probes of the Milky Way and galaxies, or as probes of cosmology. Hopefully it will sort itself out and spread evenly. But here in the room, we can do stellar astrophysics here on this side of the room, FRBs as probes of Milky Way and galaxies on that side of the room. And then if you're mostly interested in using them for cosmology, let's go to the coffee room.